Hello and welcome to this episode of Mrs. Mulvey's Math and Physics Movies. In this episode, we're going to take a continuing look at spring energy examples. So this is spring energy examples part 2. So I have a scenario where you can see I have Tiberius the moose cat. He's dropping onto a platform. So at t equals 0, Tiberius the moose cat drops from a height of h above the ground. So this is t equals 0. Tiberius safely falls until he lands on his feet on top of a weightless platform attached to an uncompressed spring of spring constant K. The spring then compresses until both it and Tiberius the moose cat come to a momentary halt at t equals t sub f. We're supposed to derive an equation for change in gravitational potential energy, delta U sub g, between t equals 0 and t equals t sub f, in terms of m, capital H, lowercase h, and universal constants. Keep in mind, when you are given these terms to use, you may not actually use all of the terms. Sometimes you will, sometimes you won't. So let's actually answer this question. This question is asking us to find an equation for the change in gravitational potential energy. I want to know how much the gravitational potential energy has changed. Well, any change like that is just the new value minus the original value. And that's going to get us the change in gravitational potential energy. So I need a new value for gravitational potential energy. After Tiberius safely lands, notice in this scenario, there is some spring potential energy, but because he still has some height, there's also some gravitational potential energy. But in this case, all we're talking about is how much did that gravitational potential energy change? And so at the end of the scenario, the gravitational potential energy possessed by Tiberius is his mass times gravity times his height, which we represent at the end with a lowercase h. This is his potential energy at the end of the scenario. At the beginning of the scenario, his potential energy was his mass times gravity times his height at that time, uppercase H. And so the change in gravitational potential energy is just the new gravitational potential energy minus the original gravitational potential energy. Now we're going to simplify this a little bit. Notice I can pull out common values of m and g, and then I have h lowercase minus capital H. And that represents the gravitational potential energy change. It started at mg lowercase h, it ended at mg uppercase h. To find a difference like that, you always take the ending value and subtract the beginning value. And so there you have Tiberius's gravitational potential energy in terms of m, there's the h, and the universal constant is g. Let's take a look at the second example, or the second question, or the second part of the question. We're supposed to get an equation for the compression of the spring, x, right here, in terms of k, m, h, and universal constants. So let's remember at the beginning of this scenario, when Tiberius first starts his trip down towards the platform, the system consists only of gravitational potential energy. Right here, once Tiberius lands and this platform is fully compressed, so fully compressed means for that moment it's fully compressed, there is no kinetic energy. The energy in the system, let me just right here, remember mechanical energy is that combination of kinetic energy and potential energy. So right now the energy in the system before Tiberius lands is mg capital H. After Tiberius lands, all of the energy in the system consists of Tiberius's new gravitational potential energy, mg lowercase h, but he also has there is also some spring potential energy. That's 1/2 kx squared. The key is that within the system, this mechanical energy always remains the same. This Tiberius spring Earth system. It's a closed system. The energy is going to stay the same. That means that these two values, my mechanical energy values, are equal to each other. So I can set up an equation that says mg capital H equals mg lowercase h plus 1/2 kx squared. And what I'm solving for is x, so I need to isolate my x. So I'm going to start by subtracting the mg lowercase h from both sides. When I do that, I end up with mg capital H minus mg lowercase h equals 1/2 kx squared. I'm going to clear out some space here from the first part of my example. I'm going to copy this down again. So that was mg capital H minus mg lowercase h equals 1/2 kx squared. Now I'm going to multiply both sides of the equation by 2. Notice both of these, everything gets multiplied by 2. And what I'm going to do here is I'm going to pull out this common factor again. So now I'm going to have the mg outside, and then I have capital H minus lowercase h, and I've got kx squared. Now I'm going to divide by k, and I'm just going to reverse the order. Since I want to solve for x, I'm just going to put my x squared on the left. That's 2 mg over k. You could keep this k below the whole thing if you wanted. However you want to write it is okay. Times h minus h. And then I would have to take the square root. Now, if you left it like this, I would accept that as well. 2mgk h minus 8. I just want to check to make sure I don't have any terms in here that I haven't been asked for. I've been asked to get x in terms of k, m, capital H, lowercase h, and any universal constants. G is a universal constant. And it looks here like I don't have any variables that haven't been mentioned, and so I'm good. There's my solution. That's it for this video. As always, if you know me or you happen to be a student of mine, feel free to contact me with any questions. And as always, I hope everybody has a fantastic day. Bye-bye.